Semigroups and their representations, Lecture 8, Generators and Relations. Let us recall the semigroup which consists of words over an alphabet. So let A be a non-empty set, which we call an alphabet. Recall that a finite word over A is an expression of the form A1, A2, and so on AK, where K is a positive integer and all AI belong to A. Note that we can repeat letters from A in a word. The set of all finite words over A is denoted by A with upper cross, and we can concatenate the words. If we have a word A1 and so on AK, we can concatenate it with the word B1 and so on BM to get the word A1 and so on AK, B1 and so on BM. And this concatenation is obviously associative, therefore A upper cross, together with this concatenation, forms a semigroup. Note that this semigroup is always infinite. For example, if we have only one letter, A, then if we take this letter as the alphabet, then the semigroup of all finite words over this alphabet is isomorphic to the semigroup of all positive integers with respect to addition, where the word A, and so on A with n letters is sent to the positive integer n. So the semigroup A upper cross has the following property. Proposition. Let A be a finite set and S a semigroup. Let G be a map from A to S. Then there exists a unique semigroup homomorphism phi from A upper cross to S, such that phi of A is equal to G of A for any A in A. Proof. Take a finite word A1, A2, and so on AK over A, and define the value of phi on this word A1 and 2 and so on AK as G of A1 times G of A2 times and so on times G of AK. Then phi, applied to the concatenation of A1 and so on AK and B1 and so on BM, equals G of A1, G of A2 and so on G of AK, G of B1 and so on G of BM. And this in turn equals to phi of A1 and so on AK times phi of B1 and so on BM. And therefore our phi is indeed a homomorphism. So this proves existence of the homomorphism, and for uniqueness we note that phi of A1, A2 and so on AK must be equal to phi of A1, phi of A2 times and so on phi of AK if phi is a homomorphism. So there should be ... here. And the latter expression must be equal to G of A1, G of A2 and so on G of AK by the condition in the formulation. And this proves uniqueness of our homomorphism. The property given by this proposition is called the free property of the semigroup A upper cross, and definition, the semigroup A upper cross is called the free semigroup over A. So we can also alternatively say that A upper cross has the property given by the following universal commutative diagram. So we have the natural inclusion map, just a set map from A to A upper cross, and now for any map G from A to any semigroup S, there is a unique semigroup homomorphism phi from A upper cross to S, which makes this diagram commutative. Next, let us talk about generating systems. Let S be a semigroup, and let B be a non-empty subset of S. Definition: we say that B is a generating system for S, provided that every element in S can be written as a finite product of elements in B. Alternative names are system of generators or set of generators. And we also say that B generates S. So if B is a generating system for S, we say that B generates S. For example, the set consisting of the positive integer 1 is a generating system for the semigroup of all positive integers with respect to addition. Indeed, if we take a positive integer m, we can write it as 1 plus 1 plus 1 and so on, plus 1, where we have exactly m summands, each equal to 1. So this shows that 1 is a generating system for this semigroup. Proposition: let S be a semigroup and B a non-empty subset of S. Then B generates S if and only if, for any subsemigroup n of S containing B, we have that n is equal to S. This should be n. N is equal to S. In other words, S coincides with the intersection of all subsemigroups of S that contain B. Proof. If B generates S and n is a subsemigroup of S containing B, then n contains all finite products of elements of B. And since each element of S can be written as such a product, it follows that n is equal to S. Let us note that the set of all finite products of elements in B is a subsemigroup of S containing B, and this implies the converse statement of this proposition. Now let us discuss a very important property of free semigroups, and that's the fact that any semigroup is a quotient of a free semigroup. So let S be a semigroup, and let B be some generating system in S. Consider the free semigroup B upper cross, and by the free property of B upper cross, there is a unique homomorphism phi from B upper cross to S, which is the identity on B. The image of phi is a subsemigroup of S, by definition containing B. And since B generates S, this means that the image of phi must coincide with S, so phi is indeed an epimorphism, or even a surjective map. And from the first isomorphism theorem, we obtain that S is isomorphic to the quotient of B upper cross by the kernel of phi. And so we can now formulate it as a corollary: any semigroup is isomorphic to a quotient of a free semigroup. Next, let us talk about relations. Let S be a semigroup, and let B be a generating system in S. Consider the surjective homomorphism phi from B upper cross to S discussed on the previous slide. Definition: the elements of the kernel of phi are called relations or defining relations. Let us recall that the kernel of phi is an equivalence relation of B upper cross, so it's a congruence in B upper cross, so the elements in the kernel are pairs A, B of elements in B upper cross. And in this context, such pairs are often written as A is equal to B, to show that this is a relation which should be satisfied in the semigroup S under the homomorphism phi. So let R be any subset of the kernel of phi with the property that the kernel of phi is the minimum congruence on B upper cross containing R. So in other words, kernel of phi coincides with the intersection of all congruences of B upper cross that contain R. Definition: in the situation above, one says that S is given by generators B and relations R. So in this case, this is called the presentation of S and is usually denoted by this symbol. So we have B and R in this triangular bracket, so we write B, then vertical line, and R on the right. So S is isomorphic to the semigroup, which is given by generators B and relations R. So for example, the semigroup of all positive integers with respect to addition is given by the presentation where we take one generator, which is 1, and no relations. This is due to the fact that 1 is a generator of this semigroup, and the kernel of the map phi from 1 upper cross to this semigroup is the equality relation, because this map is an isomorphism. So the equality relation is generated by the empty set. Next, let us discuss that every semigroup has the so-called trivial presentation. Remark: any semigroup S has a trivial presentation which is given by taking the whole of S as a set of generators and the Cayley table of S as a set of defining relations. The latter means that, as defining relations, we take all expressions of the form A dot B is equal to AB, where A and B are elements in S, and here on the left-hand side we have a word in S upper cross of length 2, it has two letters A and B, while on the right-hand side we have a word in S upper cross of length 1. AB is an element of S and we consider it as one letter. So for example, the singleton semigroup which consists just of one element, little e, will in this way get the presentation that it's generated by this e, and the relation is that e dot e is equal to e. As an example, let us discuss the presentation for monogenic semigroups. So in one of the previous lectures, we saw the so-called monogenic semigroup. So this is a quotient of the semigroup of all positive integers with respect to addition by the congruence denoted tilde m comma k, where m and k are positive integers. And the classes of this congruence are as follows. So we have singletons 1, 2, and so on, m minus 1. And then infinite classes m, m plus k, m plus 2k, and so on, m plus 1, m plus 1 plus k, m plus 1 plus 2k, and so on, and then m plus k minus 1, m plus 2k minus 1, and so on. Let us denote 1 by a to avoid confusion, so we don't confuse elements in the semigroup with elements which define the presentation. So we obtain that our quotient, our monogenic semigroup, the quotient of positive integers with respect to addition by tilde m comma k, can be given by the following presentation. We have one generator A, it corresponds to the element 1 in this semigroup, and one relation a to the power m is equal to a to the power m plus k. And this follows directly from the classification of monogenic semigroups, as our monogenic semigroup is uniquely identified by the property that a to the power m is equal to a to the power m plus k. Now let us discuss the main application of presentations, and that's a big help in solution of problems how to construct homomorphisms between semigroups. Let S and T be two semigroups. There is a natural problem: how to construct a homomorphism from S to T. The brute force approach would be to assign an element of T to each element of S and check the homomorphism property. And this is usually a lot of work. So for example, if S and T are infinite semigroups, that's kind of an infinite amount of work. So a natural question could be, is there a way to reduce the amount of work which is necessary to construct a homomorphism? And here's an idea. If we choose a generating system B in S, then any homomorphism from S to T is uniquely determined by its values on the elements of B. This is because any element of S is a finite product of elements in B. So if we know the homomorphism on B, we can use the axiom for the homomorphism to derive the value on all other elements. But then we have a new question. Assume that we assign an element of T to each element of B. What do we need to check to ensure that this extends, and if it does, that will automatically always be uniquely to a homomorphism from S to T? The answer to this is given by the following theorem. Let S be a semigroup with presentation with generators B and relations R. Let T be any semigroup and G a map from B to T. Then G extends to a necessarily unique homomorphism phi from S to T if and only if for any element in R, so we write this element in the form A1, A2, and so on, AM, comma, B1, B2, and so on, BK. So we have two words in B upper cross. We have that G of A1, G of A2, and so on, G of AM should be equal to G of B1, G of B2, and so on, G of BK. So in other words, the images of elements in B under G should satisfy the relations given by R. So we only need to check that under our choice of the map G, the defining relations for S are satisfied by the images of the elements of B under G. So if we have a short presentation, a small presentation of a semigroup, this significantly reduces the amount of work which is necessary to construct a homomorphism. For example, to construct a homomorphism from our monogenic semigroup with the generator A and relations a to the power m is equal to a to the power m plus k, to any semigroup T, we just need to pick as the image for A some element B in T such that b to the power m is equal to b to the power m plus k. And that's it. Now let us prove the theorem. The necessity of the condition is obvious, because if the relations are not satisfied, the axiom of the homomorphism cannot be true. So to prove the sufficiency, consider S, T, and G as in the formulation of the theorem. By the free property of B upper cross, there is a unique homomorphism phi from B upper cross to T, which sends an element B in B to G of B. Since we assume that the relations in R are satisfied for these images G of little b, the kernel of phi contains R, and hence also the minimum congruence tilde on B upper cross that contains R. Note that S is isomorphic to B upper cross modulo tilde, and since tilde is a subset of the kernel of phi, we can define the value of our homomorphism psi, which we try to construct from S to T, on a tilde equivalence class as a value of phi on any element of this class. This is well defined because the whole class of tilde belongs to the kernel of phi, so it belongs to one class of kernel of phi. So this value is unique. And the fact that psi is a homomorphism follows directly from the definition and the homomorphism axiom for phi. And this completes the proof. Next, let us discuss the analogous theory for monoids. Let A be a set, which we called an alphabet. We have the set A upper asterisk of all finite words over A, which include the empty word epsilon. So A upper asterisk is equal to A upper cross union with the empty word epsilon. So the word epsilon is a word with no letters of length 0. Note that if we concatenate epsilon with any word from any side, we get our word back. And this means that A upper asterisk is a monoid with unit epsilon. So this monoid has the following free proposition. Let A be a finite set and M a monoid. Let G from A to M be a map. Then there exists a unique monoid homomorphism phi from A upper asterisk, this should be asterisk, to M, such that phi of A is equal to G of A for any A in A. Let M be a monoid. Let B be a subset of M. We say that B is a generating system for M, provided that every non-identity element in M can be written as a finite product of elements in B. So for example, the set 1 is a generating system for the monoid of all non-negative integers with respect to addition. Also, this monoid of all non-negative integers with respect to addition is isomorphic to the free monoid where we have as an alphabet just 1, and then we have upper asterisk. Remark, the empty set here is allowed, and it is a generating system for the singleton monoid. And for any monoid M, both sets M and M, where we throw away the identity element, are generating systems for the obvious reasons. Now we can discuss monoid presentation. So let M be a monoid, and let B be a generating system in M. Then we have the surjective homomorphism from the free monoid generated by B to M, which extends the identity map on B, so this is due to the free property of B upper asterisk. And so by the first isomorphism theorem, M is isomorphic to the quotient of this free monoid on B by the kernel of this homomorphism phi. So the elements of the kernel are called defining relations, just like for semigroups. And for any subset R in the kernel, which generates this kernel as a congruence, we have the corresponding presentation of our monoid M, where we take B as generators and this set R as relations. And we also have a similar theorem for homomorphisms using presentation. Let M be a monoid with some presentation, generators B, relations R. So let T be any monoid and G from B to T any map. Then G extends to a necessarily unique monoid homomorphism phi from M to T if and only if for any pair of words which belong to our relation set, so we have words A1, A2 and so on AM, B1, B2 and so on BK, we have that G of A1 times G of A2 times and so on times G of AM is equal to G of B1, G of B2 and so on G of BK. So we have that the relations for M are satisfied by the images under G for the elements of B in the semigroup T. Now let us look at one explicit example. So let us consider a semigroup presentation of the semigroup T2. So that's a full transformation semigroup on a two-element set. So this semigroup consists of four elements. We have the identity transformation, which sends 1 to 1 and T to 2. We denote it by E. We have the transposition of 1 and 2. It sends 1 to 2 and 2 to 1. We have the projection pi 1 onto 1. Both 1 and 2 are sent to 1. And we have the projection pi 2 onto 2. Both 1 and 2 are sent to 2. Here is a Cayley table of this semigroup. So the identity, of course, is the identity. If we multiply identity with anything, we get that anything back. 1, 2 squared is the identity. 1, 2 times pi 1 is pi 2. 1, 2 times pi 2 is pi 1. And pi 1 is a left 0. So pi 1 times any element is equal to pi 1. This should be pi 1. And pi 2 times any element is equal to pi 2. Pi 1 is a left 0 and pi 2 is a left 0. So this should be pi 1 and this should be pi 2. Now let us observe that the set consisting of the transposition of 1 and 2 and pi 1 is a generating system for our semigroup. Indeed, the transposition squared is equal to the identity, and if we transpose 1, 2 and multiply with pi 1, we get pi 2. So we can get all other elements from these two. Some obvious relations: if we transpose again and multiply with pi 1, we get pi 1. And pi 1 times transposition is pi 1. That's because transposition square is the identity. Also, pi 1 is an idempotent, it squares to pi 1. Pi 1 times 1, 2 is pi 1. And if we take our transposition, 2 power 3, we get our transposition back. So from this we can guess that our semigroup has the following presentation. We have two generators A and B. So here A corresponds to the transposition of 1 and 2, and B corresponds to pi 1. And the relations are A cubed is equal to A squared B is equal to B, BA is equal to B, and B squared is equal to B. So to prove that this gives us a presentation for T2, denote the semigroup given by this presentation by S. Then we have a surjective homomorphism from S to T2, which sends A to the transposition of 1 and 2, and B to pi 1. And so we only need to check that S has at most 4 elements. Then it has exactly 4 elements, and this surjective homomorphism is an isomorphism. To show that S has at most 4 elements, take any word in A and B. We need to show that we can reduce it to one of the following 4 words: A squared, B, or AB. So let's start with any non-empty word W in A and B, and using that A cubed is A and B squared is B, we can reduce W to a word in which B alternates with A or A squared. Also, if there is an A on the right of B, we can use that BA is equal to B to absorb this A. And then this leaves us with exactly 5 words: A squared, B, AB, and A squared B. And then we can use that A squared B is equal to B, and then we can reduce everything to 4 words, and we are done. Also, we can note that T2 is a monoid, so we can also construct a monoid presentation of T2, and we will see the slight difference with a semigroup presentation. Of course, the semigroup presentation for T2 also works well, but for a monoid presentation we can do a little bit better and get a shorter presentation. Let's note that the transposition 1, 2 squared is equal to the identity. And identity now is a fixed element of the monoid, is a canonical element, and so we can guess that as a monoid, T2 has the following presentation. We have two elements A and B. A squared is equal to the identity, so to the identity element in the free monoid, that's our word epsilon, and then BA is equal to B and B squared is equal to B. So here the difference is that we have removed the relation A squared B is equal to B because it's now automatic, since A squared is equal to the identity. And we also changed the more complicated relation A to the power 3 is equal to A to a simpler relation A to the power 2 is equal to the identity. We couldn't use the identity previously because we didn't have a monoid. So our new presentation accounts for exactly the same relations in the previous presentation, and so it follows that it is correct. We can use the fact that the previous presentation is correct to deduce that this one is correct as well. Some problems and questions at the end. Problem question 1. Prove with all details that the minimum congruence on B upper cross containing R coincides with the intersection of all congruences on B upper cross that contain R. Problem question 2. Prove with all details that the monogenic semigroup given by the quotient of positive integers with respect to addition by the congruence tilde m comma k can be given by the presentation where we have one generator A and one relation A to the power m is equal to A to the power m plus k. Problem question 3. Find a semigroup presentation for the semigroup of all non-negative integers with respect to addition. Problem question 4. Classify all generating systems for the semigroup of all positive integers with respect to addition. Problem question 5. Prove with all details the necessity of the condition in the theorem on homomorphism via presentations. Thank you very much and see you next time.